Hello friends, I welcome you on my channel Engineering Mathematics djganit. In this lecture we are going to discuss how to calculate probabilities using standard normal tables. So before that we just recall certain things which we require. We have discussed in the last lecture that if capital X is a normal random variable with parameters mu and sigma square, then the random variable capital Z defined as Z equal to x minus mu over sigma is a standard normal random variable with parameters 0 and 1. That is, the mean of capital Z is 0 and variance is 1. Also we have discussed the cumulative distribution function of Z is denoted by phi of Z and is given by phi of Z is nothing but probability that capital Z is less than or equal to Z, which is equal to integral of PDF f of Z from minus infinity to Z, and f of Z for standard normal random variable is given by 1/2 e to the power minus z square by 2 dz. But as we have discussed in the last lecture that we are not able to evaluate this integral using usual methods of calculus. So we are not going to evaluate these integrals for calculating probabilities. Instead, we are having the table values for this cumulative distribution function of standard normal random variable. So that table is known as standard normal probability table. So in that table we are given probabilities for certain values of standard normal random variable. So we are going to use standard normal probability table for calculating this type of probabilities. Before that we make this remark. We know that this f of z is a probability density function of standard normal random variable capital Z. So if f is a probability density function, then by the definition of PDF, integral of f of z from minus infinity to infinity must be equal to 1. And we know that the definite integral represents the area under the graph of this PDF between minus infinity to infinity. So from this property we can say that the area under the density curve of f of z must be equal to 1. So as we have shown in this figure, this area is nothing but integral of f of z from minus infinity to infinity, and it must be equal to 1 always. So this means that the total area under the normal curve is unity. We have this property for cumulative distribution function of standard normal random variable, that is value of CDF at minus z equals 1 minus value of CDF at point z. So as we know by definition, phi of minus z is nothing but probability that capital Z is less than or equal to minus z. Now we know that graph of f of z is a symmetric curve about mean mu equal to 0. So the graph is symmetric, therefore we can see this area shaded by red lines, both areas are same. That is probability that capital Z is greater than Z, that is the area to the left of this small z and area to the left of this minus z are equal, as we have shown by shaded area. So from this symmetry of graph we can write by symmetry of the normal curve probability that capital Z is less than or equal to minus z is nothing but probability that capital Z is greater than z. So we observe that these two areas shaded by red lines are equal. So this area is nothing but probability that capital Z less than or equal to minus Z, and this area is nothing but probability that capital Z is greater than Z. Now by the definition, this is nothing but value of CDF at minus Z, and this we can write as 1 minus probability that capital Z is less than or equal to Z, because we know that probability that Z less or equal to small z plus probability that Z is greater than Z must be equal to 1, because Z less than or equal to Z and Z greater than Z are mutually exclusive and exhaustive events. So therefore probability that capital Z is greater than Z can be replaced by 1 minus probability that capital Z is less than or equal to small z, and this is nothing but value of CDF at point Z. So therefore we obtain that value of CDF at point minus Z is nothing but 1 minus value of CDF at point Z. So sometimes we can use this property to calculate normal probabilities. Another property is we know that probability that Z lies in the interval AB can be written as probability that Z is less than or equal to B minus probability that Z is less than or equal to A. That means the area which is shaded area here, this area is nothing but probability that Z lies in this interval. So this area is nothing but, if we consider area up to B, that is probability that Z is less than or equal to B. And to find out this area, we have to subtract area up to small a from the area up to small b. So probability that Z is less than or equal to B is the area below the graph of f up to b, and this probability that Z is less than or equal to A is the area under the graph of f up to this point A. So if we take subtraction of these two areas, we will obtain area between small a and small b. Now this is by the definition of CDF phi of b, and this is phi of A. Now we consider some examples on how to calculate standard normal probabilities using standard normal table. So before that we try to understand the standard normal table. So as you can see, this table gives us the standard normal curve areas. So this is a standard normal density curve. If we consider this small z, then the area to the left of z is nothing but probability that capital Z is less than or equal to small z. So these table values are given for this type of probabilities. These values represent the area to the left of z. Suppose I want to find out the area probability that Z is less than or equal to minus 2.73. Then I have to concentrate on minus 2.7 in the column under Z. So here I have to concentrate on this minus 2.7. I have to concentrate up to first decimal place. Now for second decimal place I have to concentrate on 0.03, or we can rewrite this as minus 2.7 minus 2.7 minus, just a minute, minus 2.7 minus 0.03. So minus 2.73 can be written as minus 2.7 minus 0.03. So we first find out this value which is below the column under Z. So minus 2.7, and on this side we concentrate on this value 0.03. So the value corresponding to minus 2.73 is intersection of this row. We have to go up to 0.03, and here we have to go up to 0.27. So this is the required value, 0.0032. So in this way we can find out the probabilities, standard normal probabilities, using this standard normal probability table. So here values are given for Z from minus 3.4 to plus 3.4. So this table is given for values of Z from minus 3.4 to plus 3.4. Suppose I want to find out probability that Z is less than or equal to 0.92. Then I have to rewrite 0.92 as 0.9 plus 0.02. So here below Z I concentrate on 0.9, and on this side I concentrate on 0.02. Okay, so here I have to first search where is 0.9 in this first column. So 0.9 is here, and I have to go up to 0.02. Okay, so this is 0.9, and here I have 0.02. So intersection of these two, that I have to find out. So you can see intersection is nothing but 0.8212. So this area to the left of 0.92 is 0.8212, or we can say that probability that Z is less than or equal to 0.92 is nothing but 0.8212. So in this way we can find out standard normal probabilities using standard normal probability table. So we consider some more examples. So we consider this example. Find the probabilities that a random variable having the standard normal distribution will take on a value between 0.87 and 1.28. That is, we have to find out the probability that 0.87 is less than Z is less than 1.28. Find the probability that the standard normal distribution will take on a value between minus 0.34 and 0.62. So in part B we have to find out this probability. Find the probability greater than 0.85 and probability greater than minus 0.65, and it is given that variable is having standard normal distribution. So we are using capital Z. So we find out these probabilities one by one. First one is probability that 0.87 is less than Z is less than 1.28. That is, Z lies in the interval 0.87, between 0.87 and 1.28. So this is the probability. This probability is nothing but this area below the graph of f between 0.87 and 1.28. So from this we can see this area is nothing but the area to the left of 1.28, that is probability that z is less than or equal to 1.28, minus area to the left of 0.87. Now this probability we can determine from the table. We have to concentrate on the z value 1.28. So we consider 1.28. We are interested in z is less than or equal to 1.28. So we concentrate on 1, 1.2 and 8. 1.28 can be written as 1.2 plus 0.08. So we have to consider 0.08 here, and in this column we have to go up to 1.2. So 1.2 is here and 1.28. So I have to go up to 0.08. Here also I have to go up to 1.2. So you can see this is the corresponding value, 0.8997. So probability that z is less than or equal to 1.28 is 0.8997. Now we are interested in z less than or equal to 0.87. So 0.87 can be written as 0.8 plus 0.07. So this is z value, and here we have to go up to 0.07. So below z we have to go up to 0.8. So this is 0.8, and here we have to go up to 0.07. So from this we go up to 0.07, and here we go up to 0.8. So the corresponding area is 0.8078. 8078. So we substitute here both the values, 0.8078, and the difference is 0.0919. So the probability that z lies in this interval 0.87 to 1.8 is nothing but 0.0919. Next one is probability that z lies between minus 0.34 and 0.62. So this we can rewrite as probability that z is less than or equal to 0.62 minus probability that z is less than or equal to minus 0.34. So we calculate these two probabilities, 0.62 and minus 0.34. So first we calculate 0.62, probability that z is less than or equal to 0.62. So 0.62 can be written as 0.6 plus 0.02. So we have to concentrate on 0.02, and in the column below z we have to concentrate on 0.6. So 0.6 plus 0.02, that is 0.62, and the intersection is 0.7324. So this value is 0.7324. Okay, so it is correct. Now we check minus 0.34. So for negative sign we have to go here, minus 0.34. So minus 0.34 means minus 0.3 minus 0.04. So this is minus 0.3, and 0.04 means this is for 0.01, this is for 0.02, this is for 0.03, and this one is for 0.04. So we can check Okay, this is 0.04. So we are below 0.04, and minus 0.34 means this is for 0, this is 1, 2, 3 and 4. So 0.3669, and the difference is 0.3655. Next one is probability that Z is bigger than 0.85. So you can see this normal probability curve. Suppose 0.85 is here, then we are interested in this area Z is greater than 0.85. So you can see this area is nothing but total area minus this shaded area to the left of 0.85. So this area is nothing but 1 minus area to the left of 0.85, that is this area. So area to the left of 0.85, which is probability that Z is less than or equal to 0.85, and area to the right of 0.85, that is probability that Z is bigger than 0.85. So sum of these two areas is 1, because total area is always 1. So therefore this area is nothing but 1 minus probability that Z is less than or equal to 0.85. So now we again go for the table 0.85. So we have to consider positive values of Z. So here we have 0.8 and we have to go up to 5. So this is for 0.01, 0.02, 0.03, 0.04 and 0.05. So we have 0.85 corresponding to Z value 0.85. The area is 0.8023. Okay, so it is correct, and the answer is 1 minus this, that is 0.1977. Next one is probability that Z is bigger than minus 0.65. So you can see this is minus 0.65 and Z is bigger than minus 0.65. That means area to the right of Z. So this shaded area is nothing but probability that Z is greater than minus 0.65. So that area can be found out by subtracting this area to the left of minus 0.65, which is nothing but this area. Area to the left of minus 0.65 is probability that Z is less than or equal to minus 0.65. So we have to write 1 minus probability of this area, that is probability that Z is greater than minus 0.65 is the area to the right of minus 0.65. So that area is nothing but total area, which is 1 minus this area to the left of minus 0.65. So 1 minus this area, and this area is nothing but probability that Z is less than or equal to minus 0.65. So in the table we concentrate on minus 0.65. So minus 0.6 and 5. So this is minus 0.6 and we have to go up to 0.05. This is 0, this is 0.01, 0.02, 0.03, 0.04 and 0.05. So it is 0.2578. So it is 0.2578 and this. Now if we don't have these values of areas for negative value of Z, then we can alternatively find as follows. So this is another way of calculating the sum probability. So here if you observe that the area to the right of area to the left of minus 0.65, this area shaded by blue lines, and area to the right of 0.65, both are equal, by the symmetry of this standard normal curve. Area to the left of minus 0.65 is the same as area to the right of 0.65. Now, area to the right of minus 0.65, probability that z is greater than minus 0.65 is nothing but 1 minus probability that z is less than or equal to minus 0.65, means this area. But this area is same as this area, so we can replace this by probability that z is greater than 0.65. We are using the fact that area to the left of minus 0.65, which is probability that z is less than or equal to minus 0.65, is equal to area to the right of 0.65, which is probability that z is greater than 0.65. So we replace this by this. Now again, probability that z is greater than 0.65 is nothing but 1 minus probability that z is less than or equal to 0.65. And if we take this negative sign inside, we have 1 minus 1 plus probability that z is less than or equal to 0.65. So if we look at the table for 0.65, so 0.65 is here, we have to go up to 5. So this is 0, 0.01, 0.02, 0.03, 0.04 and 0.05, which is 0.7422. So answer is same in both the ways. Here 0.7422, 0.7422. But we must know all the methods. Sometimes in examinations table is not given but table values are given. So suppose you have given this table value, then you have to go in this way only. Now once we know how to calculate standard normal probabilities, we can determine the normal probabilities using standard normal table. So as we know, if x is a normal random variable with parameters mu and sigma square, then z equal to x minus mu over sigma is a standard normal random variable with mean mu equal to 0 and variance sigma square equal to 1. Now suppose we want to find out this probability that normal random variable lies in interval a to b. Then this we can rewrite as, if we subtract mu and divide sigma, then this inequality can be written as a minus mu over sigma is less than x minus mu over sigma, which is less than b minus mu over sigma. Now this is nothing but standard normal random variable z, and we keep these two as it is. So as we know that this probability is nothing but probability that z is less than or equal to b minus mu over sigma minus probability that z is less than or equal to a minus mu over sigma. So this we can rewrite in terms of CDF of z as in this way: phi of b minus mu over sigma, phi of a minus mu over sigma, because we know that phi of z is nothing but probability that z is less than or equal to small z. So here instead of z we have b minus mu over sigma, here instead of z we have a minus mu over sigma. So if we are interested in calculating the normal probabilities, it is better to convert normal probabilities in terms of standard normal probabilities in this way, by standardizing the normal random variable capital X as z equal to x minus mu over sigma. So to find probabilities concerning normal random variable x, we convert its values to z scores using z equal to x minus mu over sigma. So we consider one example for determining the normal probabilities using standard normal table. Suppose x is a normal random variable with parameters 3 and 16. Find probability that capital X is positive, probability that capital X lies in the interval 2 to 5. Now it is given that X is a normal random variable with mean mu equal to 3 and variance sigma square equal to 16. Therefore sigma is nothing but 4. We know that sigma is always positive, so therefore sigma equal to 4. Now to find out this probability that x is greater than 0, we convert capital X in terms of capital Z, which is standard normal random variable. So we take x minus mu over sigma is greater than 0 minus mu over sigma. This is nothing but capital Z. Here mean mu is 3 and sigma is 4, so we put values of mean and sigma. Mu equal to 3, sigma equal to 4. Now therefore this is nothing but Z is bigger than minus 0.375, minus 3 by 4, which is minus 0.75. And this we can rewrite as 1 minus probability that Z is less than or equal to minus 0.75. That means this area is nothing but probability that Z is less than or equal to minus 0.75. And we have table values for these probabilities. Z is less than or equal to minus 0.75. So we concentrate on negative values, minus 0.7. So here we have minus 0.7 and we have to go up to 0.05. Minus 0.75 is nothing but minus 0.7 minus 0.05. So we go up to 0.05. This is for 0, this is for 0.01, 0.02, 0.03, 0.04 and 0.05. So this is the probability that capital Z is less than or equal to minus 0.75. So it is 0.2266. Okay, so it is written here and the answer is 0.7734. Now here we are interested in the probability that x lies between 2 and 5. So this is equal to probability that 2 minus mu over sigma is less than x minus mu over sigma, which is less than 5 minus mu over sigma. This is nothing but standard normal random variable, so we replace it by z, and here we put values of mu and sigma. So probability that 2 minus 3 by 4 is less than z less than 5 minus 3 by 4. So after simplifying we obtain this probability is nothing but probability that z lies between minus 1 by 4 and 1 by 2. That is, z lies between minus 0.25 and 0.5. So it can be seen in this graph. Z lies between minus 0.25 and 0.5. So this probability is nothing but this shaded area. So to calculate these probabilities, first we calculate the area to the left of 0.5. But to obtain this area, we have to subtract area to the left of minus 0.25 from the area to the left of 0.5. So this I can write as probability that z is less than or equal to 0.5 is minus probability that z is less than or equal to minus 0.25. And every time it is not necessary to sketch this standard normal curve, and this is just for understanding. Otherwise you can remember this probability that A lies in probability that z lies in this interval a to b is nothing but probability that z is less than or equal to b minus probability that z is less than or equal to a. So using this we can see here b is 0.5, so probability that z is less than or equal to 0.5 minus probability that z is less than or equal to minus 0.25. Now z is less than or equal to 0.5 means I have to concentrate for positive z values 0.5. So this is 0.5 and we have to go in this column 0.50, that is 0.6915. So this is 0.6915. Here z is less than or equal to minus 0.25. So we come to the negative values minus 0.25. So here we have minus 0.2 and we have to go up to 0.05. So this is 0, 0.01, 0.02, 0.03, 0.04, 0.025. So probability that z is less than or equal to minus 0.25 is 0.4013. Okay, so which is written here, and the difference is 0.2902. So in this way we can use standard normal probability tables to find out the values of probabilities, either for standard normal random variable or normal random variable, and we have used this fact so many times. Instead of x we are using z. So this is equal to probability that z is less than or equal to b minus probability that z is less than or equal to a. Also we have used this fact, probability that z is greater than a is equal to 1 minus probability that z is less than or equal to a. Okay, so these two we have used so many times, and it is not easy to understand these two properties which we have discussed in the lecture on probability density function. So in the next lecture we will do some more examples on normal probability distribution. So I hope you like this lecture. If you are watching this lecture first time, kindly subscribe this channel for upcoming lectures of each mathematics subject of engineering. Thank you very much.